What's up, guys? Welcome back to my YouTube channel. Finally getting to do this video. Is the most requested video ever. But yeah, so this is Draw My Life. And, it all started with my mom and dad. She told me that they met each other on an app called Ponder. I don't really know what that is, but they fell in love with each other, and they had me. Hi, I'm Toad, and this is the story of my life. So exactly about like 5 seconds after I was born, my dad said he needed to go to the grocery store and get some milk. I don't really know what that is, but he hasn't really came back since. So, I don't know. And out of nowhere, this guy came out from a tree, and he told me his name was Dr. Armour, and he was like, "Hey, kid, you want to go to college for free?" And I was like, "For free? Yo, bet." And he said, yeah, he'll send me 2 escorts to escort me to UCSD in like 2 days. Oh, shit. Oh, they're here a little bit early, huh? Hi. Where am I? You guys ready to dissect? Let's go.
Hi everyone, we're Group 9. Our projects focus on the effects of adenosine, ADH, and histamine on systemic circulation and capillary exchange in frog model. Capillary is responsible for the exchange of fluid and nutrients between the blood and interstitial tissue. In clinical practice, adenosine and histamine are known for vasodilation, while ADH is for vasoconstriction. However, little is known about their effects on frog systemic circulation and capillary exchange. This study investigated the effects of adenosine, ADH, and histamine on the change in frog rate and drip rate.
So for our materials, we have our 1 frog, and then for our treatments, we have our control, which is our 3% ringus and dextran solution. Then we also have, for our experimental drugs, we have the 2 millimolars of adenosine in the ringus and dextran solution, 1 microgram per milliliter of ADH in the dextran and ringus solution, and finally our 1 millimolar of histamine also in the ringus and dextran solution. For our calibration, in order to get our calibration equation of our isometric transducer, we took 5 10-gram weights, added it to the weight pan of the isometric transducer, and then we use a linear regression to find the relationship and conversion of the transducer recording into weights. So our equation turns out to be weight in grams equals to 4.976 grams per millivolts times our transducer recording. And we take our raw data and took the linear regression of that raw data to find the change in transducer recording. And then we plug this back into our calibration equation to get our change in weight. In our setup, we have a frog hooked onto the isometric transducer with the catheter placed in the left branch of the atrium, the funnel placed 24 centimeters above the frog heart with the transducer supply plugged into the power amp and then into the power lab.
Through Ohm's laws of flow rate and resistance, as well as Starling's law of ultrafiltration, relationships between blood vessel radius, flow rate, which is measured by drip rate, and net water movement and capillary exchange can be established as demonstrated by its diagram. Flow rate has an inversely proportional relationship with total peripheral resistance, which itself has an inverse relationship with blood vessel radius. This means that although an increase in radius would reduce the total peripheral resistance, this in turn would cause an increase in flow rate. Thereby, we can expect an increase in drip rate in this hypothetical scenario. Additionally, flow rate directly determines capillary pressure as arterioles are located upstream of capillaries. If arterioles vasodilate, more blood can flow through to the capillaries, which exerts more hydrostatic force against the capillary walls from the inside, pushing water out of the capillaries and into interstitial tissue. Likewise, capillary pressure is one of the 4 factors affecting net water movement, but in the context of this study, it's the only variable that will be affected by the agents that we introduce. Weight gain is expected with a positive coefficient as net water movement towards interstitial tissues, vice versa. In this study, we assume that concentration at which our agents are introduced only bear a negligible effect on viscosity and any oncotic pressures. Length remains constant because the systemic circuit itself does not grow. The driving pressure is constant as well as we maintained a constant fluid volume and funnel input height.
When GQ pathway is activated, the G-alpha-Q subunit splits from the complex and activate phospholipase C, also known as PLC. PLC can cleave phosphatidylinositol biphosphate into diisoglycerol and inositol triphosphate. IP3 binds to IP3 receptor, which is a calcium channel on the sarcoplasmic reticulum, and induce a calcium influx into the cytosol. DAG, on the other hand, can activate protein kinase C. Activated PKC can phosphorylate L-calcium channel and increase its activity, bringing more calcium from the extracellular space. PKC can also downregulate the activity of potassium channel by phosphorylation, therefore delaying the repolarization phase of the fascicular smooth muscle. In this case, the voltage-dependent LTCC can stay activated longer and let more calcium into the cell. Intracellular calcium can bind to calmodulin, and the complex of calcium and calmodulin can activate myosin light chain kinase. MLCK uses ATP to phosphorylate myosin and activate its ATPase. Myosin heads with activated ATPase can then interact with actin and form cross bridges, ultimately resulting in smooth muscle contraction.
In the GS transduction pathway, a ligand binds to the receptor of the GS protein, and GS protein then becomes activated, and this causes the G alpha subunit to split off from the G beta and G gamma subunit to activate adenyl-cyclase, and adenyl-cyclase then takes ATP and creates cyclic AMP from it. The cyclic AMP then goes on and activates protein kinase A, which can then phosphorylate many different proteins. One of the proteins that pKa phosphorylates is the myosin light chain kinase, and pKa actually prevents and inhibits the MLCK from phosphorylating the myosin heads and turning its ATPase active. pKa also goes on and phosphorylates the myosin light chain phosphatase and actually increases its activity to remove the phosphate heads and make the myosin ATPase inactive. Then pKa goes on to phosphorylate potassium channels and decreases and lowers its threshold potential and allows for potassium to exit the cell a lot sooner, since it's activated a lot quicker. And this quickly repolarizes the cell and causes the L-type calcium channels to close up a lot quicker and prevents calcium from further entering the cell. This overall lowers the cross-bridge formations from less myosin ATPase being active, and with less calcium entering the cell and activating MLCK, this causes a net relaxation of the smooth muscle.
The mechanism underlying the GI signal transduction pathway is dichotomous to that of the GS pathway. Therefore, it will ultimately result in vasoconstriction. In the initiation of this pathway, a ligand will bind to its respective receptor, which is coupled with a GI complex consisting of alpha, beta, and gamma subunits. Upon its binding, the complex will undergo a conformational change, releasing the alpha subunit from the complex, allowing it to downregulate adenylate cyclase. Because adenylate cyclase is naturally responsible for catalyzing conversion of ATP to cyclic AMP, inhibition of adenylate cyclase mitigates cyclic AMP production. Thereby, effects opposite to those of the GS pathway can be observed, an upregulation of MLCK alongside downregulation of both MLCP and potassium channels. As a result, less relaxation occurs and there will be higher concentrations of phosphorylated myosin, increasing contractile recruitment. In turn, this greater contraction within vascular smooth muscle corresponds with decrease in the blood vessel radius. The first treatment we introduced to this frog was adenosine. There are 4 types of adenosine receptors present throughout the human body: A1, A2A, A2B, and A3 receptors. All these receptors are also present in the vascular smooth muscle tissue in the systemic circuit, and thereby induce vasoconstriction or vasodilation upon activation. Both the A1 and A3 receptors are coupled with GI signal transduction pathways and likewise induce vasoconstriction. Activation of A2B receptors also results in vasoconstriction, though they're instead coupled with GQ pathways, whereas A2B receptors are the only adenosine receptors that induce vasodilation as they're coupled with GS transduction pathways. When it comes to our results, we observe decreases in both drip rate and weight change, which function as measures of flow rate and water flux respectively. This thereby means that flow rate throughout the systemic circuit decreased and that net water movement towards the capillaries increased, as marked by a decrease in the Starling filtration coefficient. Though despite this negative change in the rate of weight change, net water movement is still towards interstitial tissue, but just less so. Because we observed a decrease in drip rate and rate of weight change, it is evident that there is a net vasoconstrictive effect, as all other potential variables that affect total peripheral resistance and flow rate are held constant. Only a reduction in lumen radius could produce these effects. Thereby, it can be concluded that there is a greater combined presence of A1, A2B, and A3 receptors relative to A2A receptors. Granted, there may not be relatively equal amounts of A1, A2B, and A3 receptors in the vascular smooth muscle tissue of this frog, but when combined, certainly exceed the amount of A2A receptors.
There are 3 ADH receptors in the human body. The first one being the V1 receptors. They are mainly present in the vascular smooth muscles, and these receptors activate the GQ protein and triggers the GQ transduction pathway that leads to vasoconstriction of the arterioles as mentioned earlier. The second being the V2 receptors, and these are mainly expressed in the kidneys, but there are also some present in the vascular smooth muscles, and they trigger the GS protein and the GS transduction pathway, which leads to vasodilation. V3 receptors are not present in the vascular smooth muscles and therefore have no effect on the vasoconstriction nor vasodilation of arterioles. So in our data, we saw a decrease in both the drip rate and changing weight. A decrease in drip rate corresponds to a decrease in flow rate, and a decrease in the change in weight corresponds to more water flux going towards the capillaries from the interstitial tissues compared to before. But the net water movement is still going towards the tissue since the change in weight is positive, but it is increasing at a slower rate. This could be due to the fact that there were more V1 receptors activating in the frog vascular smooth muscles than V2 receptors. Since V2 receptors are still active, but there's just a higher ratio of V1 to V2 receptors being activated. So the overall net effect leads to vasoconstriction. Vasoconstriction leads to a decrease in capillary pressure and will lead to a decrease in water flux, and will ultimately lead to a decrease in the rate of change in the frog weight. Vasoconstriction decreases the radius of the arterioles, which then increases the overall resistance in the circulatory system, which lowers the volumetric flow in the Ohm's law and causes a lower drip rate, as discovered in the results above.
Next, we investigated the effects of histamine on the rate of weight change and drip rate. There are 4 G protein-coupled receptors that can interact with histamine. However, only H1 receptor and H2 receptor are present on the vascular smooth muscle. H1 receptor can activate the GQ transduction pathway and trigger vasoconstriction, while H2 receptor can trigger vasodilation through GS pathway. Our results show a decrease in both the drip rate and the rate of weight change with the application of histamine. The decrease in drip rate indicates that the flow rate of the frog systemic circulation is lower. The decrease in the rate of weight change reflects that there is less water flow into the interstitial tissue. However, despite the negative value of delta in the rate of change compared to the control, the net water flux is still towards tissue as the phi remains positive. Our results can be explained by a net effect of vasoconstriction. When the arterioles constrict, less blood is able to flow into the capillary, leading to a decrease in the capillary pressure. According to the starting equation, a smaller capillary pressure will result in a smaller phi with all the other parameters being constant. Therefore, the rate of weight change decrease as shown in our results. On the other hand, vasoconstriction can also lead to a smaller vessel radius. Using the Ohm's law, we can predict a high resistance, thus leading to a smaller volumetric flow, which also resonates with our results. From the previous slides, we showed that H1 receptor can induce vasoconstriction, while H2 receptor can cause vasodilation. Considering our results, it is possible that more H1 receptors are present on the frog vascular smooth muscle than H2, causing a net effect of vasoconstriction. In summary, adenosine, ADH, and histamine all induced a net vasoconstriction in the frog model since a decrease in both the drip rate and the rate of weight change was observed. Comparing with the findings that focused on human patients, adenosine and histamine have shown an opposite effect. With the knowledge of these effects of these drugs, more caution should be made when developing medicine.